Okay, so we're going to talk about our first method for solving differential equations, and this is going to be pretty easy for people who remember Calc 1 and Calc 2. So here we go. If we have a differential equation that looks like this, and the important part about it is that the derivative of y with respect to x is just a function of x. There's no y's over here. Then this is just saying that the derivative of y is this function, and of course if I want to solve for y, that means that y is going to be the antiderivative of this function, or more precisely, I want the general antiderivative, so this is where we put plus c. C could be anything here, c could be any constant, and we call this the general solution to the differential equation, because usually a differential equation without additional information, it has infinitely many solutions, and this expresses all of the solutions. You could choose whatever value of c you like, and that gives you a solution. If you do have another piece of information, and more specifically what I mean is, so first of all, this is the same exact differential equation from before, but the extra piece of information is this. This is a initial value. In particular, we're told that y of a certain number equals a certain other number. And if we're given that piece of information, then we can actually solve for c. There will only be one value of c that actually satisfies this part, and we call that a particular solution. Anyway, like I said, this should be easy. I'm going to do an example. This is, if anything, this is mostly just practice, remembering antiderivatives once we do this. So here we go. Here's a differential equation, and it's like I put before, dy over dx is only a function of x. I don't see any y's over here. So let's do the antiderivative. So, of course, the way to do this is to call this x to the minus 2, and then we use the normal rule. This is, I increase the power by 1, and then I have to divide by that same number, the new power, and at this point I should put plus c. Let me maybe clean this up a little bit. So this is a negative sign, and this is 1 over x. Oh, whoops, I forgot the negative. There we go. Okay, and if I didn't have this piece of information, then I would just say I'm done. I would say there's infinitely many solutions, and this expresses all of them. But I do have this piece of information, so this should allow me to narrow it down to one particular value of c. So the way this goes, this is telling you the x value, this is telling you the y value. So I put in 5 here, I put in 1 for x, and then we can solve for c. C is going to be 6, and then finally I just rewrite my old answer from before, except now that I know c, I'll put 6. Pretty easy. You've probably even done things exactly like this before, but we're at the beginning of class, so we're starting with easy stuff. So let me do something like a physics problem. And again, this is not going to be particularly hard. This is, if you're in differential equations class, you've probably done things like this in physics and even previous calculus classes. But it is an example of the type of differential equation that we're talking about technically. So here we go. We have a car that is initially traveling 88 feet per second, and then it hits the brakes. And between the time that we hit the brakes and the time that we stop, the distance that we skid is 176 feet. And let's assume that the acceleration is constant when we're hitting the brakes. And the question is, how many seconds does it take the car to stop? So, like I said, we're going to use differential equations for this. And again, these are all, as far as differential equations go, these are pretty easy ones. But the thing to remember is that the derivative of position, typically we use s for position. The derivative of position is velocity, and the derivative of velocity is acceleration. So here we go. So what are we given? Maybe let me start with acceleration. The acceleration is constant. So I'm going to say a of t is, I don't know, maybe I'll call it like capital A. So I don't know, so let me start that over. This tells me basically everything I would ever want to know about acceleration. What I would like to do is sort of start working my way up. When I say working my way up, I mean I'm going to use acceleration to talk about velocity. And then once I know velocity, I'll use that to talk about the position. Anyway, I should probably go faster because you might be bored. So derivative of velocity is this capital A, because that's acceleration. And I'm just going to sort of make a point out of setting up my little initial value problem, even though it's so easy. Here's my derivative of v with respect to t. I would like an initial value, so I know the velocity at time 0 is 88. So let's solve this. So this is the type of differential equation that we just learned to solve. So the point is that the letters are switched around, but the point is that the right-hand side doesn't involve t. So I'm just going to take an antiderivative. And this is so easy because I'm doing the antiderivative of a constant. Antiderivative of a constant is just that constant times t. But when I do this, I should introduce a new constant. And this is where, maybe I'll call this v of t. It doesn't really matter, but I should be able to solve for this. So v of 0 is 88, so I put in 88 here, and I put in 0 for t. So c is 88. All right, so like I said, we're working our way up. So now let me use this to work my way up. First of all, v of t is at plus 88. Let me plug that in here. So ds over dt is at plus 88. And let's make sure to set up an initial value problem. So I would like to know the position at time 0. The problem doesn't really say anything about this, so we sort of get to choose our reference point, right? Why don't we say that the position when we start hitting the brakes is 0, just for convenience? And we'll have to remember that we made that arbitrary decision. So when we say we skidded 176 feet, that means away from position 0, because we just sort of arbitrarily said that we're starting at position 0. Anyway, let's solve this. This is just another antiderivative. And again, the point is there's no s's over here. So I just take the antiderivative. This is 1/2 at squared plus 88t plus another constant. I don't want to use c again, so I'll just use the next letter in the alphabet. And let's use this piece of information. So 0 goes in for s, 0 goes in for t, and I'm just going to get 0 equals d. Okay, But let me take a step back and try to actually answer the question. I just sort of launched into this solving differential equations mode. The actual question was, how many seconds does it take the car to stop? So let's try to answer that. I know, yeah. So when the car stops, that means the velocity is 0. So I can solve this for t. Of course, I don't really have a very satisfying answer right now because it depends on A. I would like to get a specific number here, not something that depends on A, but I haven't used all my information yet. The one piece of information that I haven't used yet is how far the car skids. I haven't done anything with this number, 176. I should do something with this number. So what do I know? I know that at that time, meaning that the time when the car stops, the distance traveled is this number. That's how far that the car has skidded. So S of t, which, yeah, jumping all over the place here. S of t, for that value of t, oops. Why did I do that again? Okay, there we go. I successfully wrote 1/2 that, and then I'm just doing S of that value of t. So I'm copying this down and replacing all the t's with that. Okay, let me simplify this. So, all right, 88 squared is 7744, and then what's half of that? 3782. So I've got a negative 3782. Because that's 1/2 of 88 squared. Oh no, it's positive because it's squared. And then I've got an a and then an a squared. So one of those cancels and I've got an over a here. And then 88 times 88 is 7744 over a. And then these are like terms. In fact, this number is actually just half of that number, so I get negative 3782 over a. Okay, what were we doing? I just spent a minute simplifying this. We were saying that at the time that the car stops, which I plugged it in and we got the position at that time, but we know what that position is supposed to be. We know that's supposed to be 176. That's the distance the car skid. So this is going to let us solve for a, and then I can plug that value of a in there, and that'll give me a numerical answer for t, and then we'll be done. Let me just show my work here. These numbers are kind of big, so just trust me on this. A is negative 22. And yeah, maybe I should be good and show my units here. This is acceleration. This should be, the unit should be like distance over time squared. Distance is in feet, time is in seconds, just in case we want units on this. But anyway, t is this, so 4 seconds. So the car was skidding for 4 seconds.